Imagine trying to have a conversation between two people who speak completely different languages. Not just different languages, but languages that operate on entirely different laws of physics. Languages so fundamentally incompatible that no amount of effort, no amount of clever software, and no amount of engineering creativity had ever successfully bridged the gap between them. One person speaks the language of classical computing. Zeros, ones, transistors, binary logic. The same digital language that has powered every single computer on Earth for the last 70 years. From the first room-sized mainframes to the smartphones in your pocket to the data centers running the world's most advanced artificial intelligence systems, everything runs on this same foundation. It is reliable, it is scalable, and humanity has spent 7 decades learning exactly how to push it to its absolute limits. The other person speaks an entirely different language, the language of quantum mechanics, superposition, entanglement, qubits, probability clouds, and calculations that do not just exist in one state at a time, but in multiple states simultaneously. This is not a metaphor or a simplification. This is the actual physical reality of how quantum systems behave, rooted in the deepest laws of nature that physicists have been studying for over a century. For decades, these two worlds could not talk to each other in any meaningful way. They could not share information efficiently. They could not collaborate on the same problem in real time. A quantum processor sitting right next to the most powerful GPU supercomputer on Earth was practically useless as a partner, like a foreign diplomat placed in a critical negotiation with no interpreter in the room, full of knowledge and capability, but completely unable to communicate it. The two systems existed in parallel, each doing its own thing with no real bridge between them. Then NVIDIA walked in with a solution. A bridge. They called it NVQ Link. It launched in October 2025, and now 1 full year into its existence, the entire computing world is asking one simple but enormously important question. Did it actually work? The answer is not just yes. The answer is yes, in ways that nobody fully anticipated, in ways that surprised even the researchers closest to the project, and in ways that have fundamentally shifted the timeline for when quantum computing becomes genuinely useful to science and industry. And by the end of this video, you're going to understand exactly what happened, why it matters more than almost any other technology story of the past year, and what is coming next because of it. To understand why NVQ Link is such a big deal, you first need to understand the problem it was built to solve. And that problem goes far deeper than most technology coverage ever bothers to explain, because the surface-level explanation of quantum computing, that it is faster and more powerful, completely misses the real engineering challenge. Quantum computers are extraordinarily powerful in theory. They process information using qubits. Unlike classical bits, which must be either a 0 or a 1 at any given moment, a single qubit can exist in a superposition of 0 and 1 simultaneously. This means a quantum system with even a modest number of qubits can represent and process an astronomical number of possible states at the same time. Quantum systems can explore an enormous number of possible solutions to a problem in parallel rather than one at a time. Entanglement makes this even more powerful, creating a connection between two qubits so that the state of one instantly determines the state of the other, regardless of the physical distance between them. These properties give quantum systems a fundamental computational advantage over classical machines for certain specific and important classes of problems. Simulating molecular behavior for drug discovery, optimizing enormously complex logistical systems, breaking certain types of encryption, training specific architectures of machine learning models. The potential is real, and the scientific community has understood it for decades. But here is where the brutal engineering reality comes in. Qubits are extraordinarily fragile. They lose their quantum state through a process called decoherence, and they lose it fast. Even the tiniest fluctuations in temperature, a stray electromagnetic field passing through the room, a small mechanical vibration in the floor beneath the machine, any of these can destroy the quantum state of a qubit and collapse the entire calculation in progress. This is why quantum computers today operate at temperatures colder than outer space, inside heavily shielded enclosures, with enormous amounts of engineering effort devoted entirely to keeping the qubits isolated from the noisy physical world around them. And even with all of that protection, qubits still make errors constantly. This is not a flaw that better engineering will eventually eliminate. It is a fundamental property of quantum systems. The errors are intrinsic, and this means that quantum error correction is not an optional feature. It is an absolute requirement for any quantum computer that hopes to produce reliable results on meaningful problems. Without error correction, the noise overwhelms the signal and the computation becomes worthless. Here is what makes quantum error correction so brutally difficult. It must happen in real time, at microsecond speeds. The quantum processor is generating errors constantly as it runs. The correction system has to detect those errors and send corrective signals back to the quantum processor faster than new errors accumulate. If the correction loop is too slow, the errors pile up faster than they can be fixed, and the whole system fails. On a standalone quantum processor with no external computing support, achieving this correction loop at the required speed is nearly impossible with current technology. The correction algorithms are computationally complex. Running them fast enough on the quantum processor itself while the processor is also trying to do useful work is like trying to fix a car engine while simultaneously driving it at full speed down a highway. What you actually need is a powerful classical computer sitting right next to the quantum processor, dedicated entirely to running the error correction algorithms in real time, processing the error signals from the quantum processor, computing the necessary corrections, and sending those corrections back with almost no delay. The connection between the classical computer and the quantum processor has to be fast enough that the correction signals arrive before the quantum state degrades further. This connection, this bridge, is what nobody had successfully built at the scale and speed required. Until NVIDIA. October 28, 2025, GTC Washington, D.C. Jensen Huang walked onto the stage and made the announcement himself, and his framing of it was deliberate and precise. He called NVQ-Link the Rosetta Stone connecting quantum and classical supercomputers, uniting them into a single coherent system, and marking the beginning of the quantum GPU computing era. And then he said something that should have been a headline in every major publication on Earth. He said that in the near future, every NVIDIA GPU scientific supercomputer will be hybrid, tightly coupled with quantum processors to expand what is computationally possible. Not some supercomputers, not specialized research machines accessible only to a handful of elite institutions. Every GPU scientific supercomputer on Earth. That is the scale of the transformation NVIDIA is engineering, and it is worth pausing for a moment to let that sink in. And if you are starting to see why this matters, hit that like button and subscribe right now, because we are about to go much deeper. But a press conference is one thing, real engineering results are another. So let us walk through exactly what happened in the 12 months that followed that announcement, because the results tell a story that is even more impressive than the launch. The first thing NVIDIA did was bring in partners, and not small or experimental ones. From the very first day of the NVQ-Link announcement, 17 quantum hardware companies signed onto the program. These included IonQ, Rigetti, CQC, and Silicon Quantum Computing, collectively covering multiple different qubit architectures, including superconducting qubits, trapped ion qubits, spin qubits, photonic approaches, and neutral atom systems. This diversity was not accidental. It was a critically important strategic design choice that reveals something essential about how NVIDIA is approaching the quantum computing market. NVIDIA did not build NVQ-Link to work with only one type of quantum computer. They did not bet on a single qubit architecture the way Google, IBM, and Microsoft have each made their own separate bets. They built NVQ-Link as a universal interconnect, one system capable of linking GPU supercomputers to any quantum processor regardless of what physical technology that processor uses. This means that as the quantum computing field continues to evolve, as some architectures prove more capable than others, as new approaches emerge that nobody has yet invented, NVQ-Link remains relevant and valuable across the entire landscape. 5 quantum control system builders also joined from the beginning, including Q-Control, Qubit Control, and Zurich Instruments, whose hardware sits between the quantum processor and the classical computer, and handles the physical translation of signals from the digital world into the precise microwave pulses and laser signals that actually manipulate qubits. And 9 of the most important and credible scientific institutions in the United States signed on immediately: Brookhaven National Laboratory, Fermilab, Lawrence Berkeley National Laboratory, Los Alamos National Laboratory, MIT Lincoln Laboratory, Oak Ridge National Laboratory, Pacific Northwest National Laboratory, Sandia National Laboratories. These are not experimental partners brought on for appearances. These are the institutions that built the atomic bomb, mapped the human genome, discovered the Higgs boson, and currently run the fastest supercomputers open to scientific research anywhere on Earth. When institutions of this caliber sign onto a technology program within days of its announcement, it sends an unmistakable signal to the rest of the scientific community. NVQ-Link was not vaporware. It was something worth building on immediately. By November 2025, less than a single month after the launch, the momentum had already gone global. NVIDIA announced that more than a dozen supercomputing centers and national research institutions across Asia and Europe were joining the program. What had started as a US-led initiative became a globally coordinated infrastructure project within weeks of its announcement. The speed of this adoption was itself remarkable and told you something important about the state of the quantum computing field. Researchers and institutions around the world had been waiting for exactly this kind of bridge technology, and when it arrived, they moved fast. And this is the moment where the first real benchmark result showed up, and it was not just good, it was a world record. Like and subscribe right now, because this is where the technical results get genuinely shocking. Quantinuum, widely considered one of the most technically serious quantum computing companies in the world, integrated their Helios quantum processor with NVIDIA GPUs through NVQLink. And using this connection, they achieved something that had never been accomplished before in the entire history of quantum computing. They demonstrated the world's first real-time use of a scalable decoder for a class of quantum error correction codes known as QLDPC codes, which stands for Quantum Low-Density Parity Check codes. To understand why this matters so much, you need to know what QLDPC codes actually are and why the quantum computing field cares about them so deeply. These are a class of error correction approach that theoretical physicists and computer scientists have believed for years could be dramatically more efficient than the surface codes that most quantum computers currently rely on. Surface codes work, but they are extremely resource intensive. To protect a single logical qubit, the kind of qubit you actually use to do useful computation, surface codes require hundreds or even thousands of physical qubits running error correction in the background. This overhead is enormous, and it means that building a truly fault-tolerant quantum computer using surface codes requires an almost unimaginably large number of physical qubits. QLDPC codes theoretically offer a much better ratio, much less overhead, far more efficient use of physical qubits to protect logical qubits. But running QLDPC decoding fast enough to keep pace with real qubit errors in real time had seemed practically impossible before NVQLink. The algorithms are more complex, and the speed requirements are even more demanding than surface code decoding. NVQLink solved this problem. The Quantinuum system achieved a round-trip error correction time of just 67 microseconds. To put that in perspective, the Helios quantum processor required a reaction time of 2 milliseconds to function correctly. NVQLink delivered corrections 32 times faster than required. 32 times. That is not barely meeting the engineering requirement. That is obliterating it with enormous margin to spare, and that margin matters enormously because it means there is headroom to scale to larger, more complex quantum processors without immediately hitting latency limits. The technical specifications that made this possible are worth understanding in detail because they reveal the engineering elegance at the heart of NVQLink. The system delivers 40 petaflops of AI performance at FP4 precision. Its throughput from GPU to quantum processor reaches 400 gigabits per second. And its end-to-end latency sits below 4 microseconds for a complete round trip. This is achieved through a networking approach called RDMA over Converged Ethernet, which allows the GPU to read from and write directly to the quantum control system's memory without routing the data through the main CPU first. Eliminating that CPU routing step removes a critical source of delay and is a large part of why the latency numbers are so impressive. And because NVQLink uses standard Ethernet infrastructure rather than exotic proprietary cables or custom connection hardware, it is straightforward to scale and expand as quantum processors grow in size and complexity over the coming years. That choice to use Ethernet is a hallmark of genuinely good engineering, solving an extremely hard problem with tools that already exist, that already work reliably at massive scale, and that the industry already knows how to deploy and maintain. As 2025 turned into 2026, the ecosystem around NVQLink kept expanding in ways that showed just how seriously the quantum computing community was taking this technology. At GTC 2026 in March, the full scale of Q-Day Q adoption, the software platform that runs on top of NVQLink and provides the programming interface for hybrid quantum classical applications, became clear for the first time. Scaleway, a major European cloud provider, began supporting Q-Day Q kernels from its Quantum as a Service platform, making hybrid quantum classical computing accessible to researchers who do not have physical access to quantum hardware. PSI Quantum integrated Q2Q with its construction platform for simulating large-scale fault-tolerant hybrid applications. Pascal integrated Q2Q with its quantum resource management interface, enabling scheduling of work across multiple quantum processors and classical computing resources simultaneously. TII integrated its Chibok framework with Q2Q for hybrid workload validation. And AMMQ announced an extensible distributed quantum compiler built entirely on Q2Q, demonstrating for the first time how hybrid applications could be intelligently distributed across multiple quantum processors running in parallel, simulating computational tasks at scales that would have been completely impossible just 12 months earlier. Then Seneca and Chipu Quantum did something that made researchers around the world stop and pay attention. They ran what is believed to be the largest known state vector simulation of a quantum optimization routine ever attempted anywhere. A 43-qubit simulation of a new algorithm called quantum-enhanced memetic taboo search running simultaneously on 2048 NVIDIA Ampere GPUs working together. This simulation targeted a challenging class of combinatorial optimization problems called low autocorrelation binary sequences, which have direct practical applications in signal processing and wireless communications. This was not a demonstration for its own sake. It was proof that NVQ Link and CUDA-Q were not just working in theory. They were enabling real computational results at the absolute frontier of what hybrid quantum classical systems can currently achieve. In April 2026, NVIDIA took another major step that almost nobody had predicted, and it may ultimately turn out to be the single most important thing they did during the entire first year of NVQ Link. They launched Ising, named after the landmark Ising model from statistical mechanics, a mathematical framework that transformed our understanding of phase transitions and complex physical systems. NVIDIA Ising is the world's first family of open-source AI models, built specifically and exclusively for quantum computing applications. And the results it delivered immediately were genuinely staggering. The Ising toolkit directly addresses two of the most crippling practical bottlenecks facing quantum computing today. The first is calibration. Every quantum processor requires regular, intensive, and highly specialized manual calibration to keep its qubits behaving consistently and producing reliable results. As quantum systems grow larger and more complex, with more qubits and more sophisticated control systems, calibration becomes an increasingly enormous time sink. For many quantum computing systems today, calibration takes multiple days of work by highly trained PhD-level quantum physicists before the machine is ready to run experiments again. This means quantum computers spend a significant fraction of their operational time sitting idle while experts work to bring them back into calibration. That is an enormous waste of an enormously expensive resource. Ising calibration is a 35 billion parameter vision language model trained specifically on quantum hardware data. It reads the experimental measurements coming from a quantum processor and automatically infers exactly what adjustments are needed to bring the system back into proper calibration. With an AI agent running Ising calibration, the time required to bring a quantum processor from an unstable or drifted state to a fully calibrated operating state drops from multiple days down to just a few hours. This is not a modest efficiency improvement. This is a fundamental change in the economics and availability of quantum computing hardware. A quantum computer that can be recalibrated in hours instead of days is a quantum computer that spends far more of its time actually running research and far less time sitting idle. That directly translates into more scientific output per dollar of investment and faster progress across every field that quantum computing touches. The second bottleneck the Ising toolkit addresses is real-time error correction decoding. Ising decoding delivers performance up to 2.5 times faster than pi matching, which is the current open-source industry standard decoder used by virtually every quantum research group in the world. Beyond raw speed, Ising decoding achieves up to 3 times higher accuracy than pi matching, while simultaneously requiring 10 times less training data to reach those results. Hit that like button and subscribe right now, because what I am about to tell you is one of the most quietly significant technology facts of 2026. Independent benchmarks confirm that Ising calibration is not just the best quantum calibration AI model that NVIDIA offers. It is the best quantum calibration AI model that currently exists anywhere in the world, outperforming every general-purpose language model and every specialized system that has been tested against it on the Q-CTRL quantum calibration evaluation benchmark. This is a system that genuinely understands quantum hardware at a level that no general-purpose AI has previously achieved. Real-world deployments moved quickly to confirm that these benchmark numbers translated into actual practical results. AGIC, a photonic quantum computing company with hardware installed at the UK's National Quantum Computing Centre, integrated Ising calibration into the daily operational workflow of their first-generation photonic quantum computer called Artemis. The result was a 3 times reduction in the engineering time their team spent on calibration work every single week. Tasks that previously demanded senior quantum physicists with years of highly specialized expertise could now be handled by engineers without deep quantum physics backgrounds. This is a breakthrough in the practical deployment of quantum hardware that deserves far more attention than it has received. One of the most persistent and underappreciated barriers to deploying quantum hardware at scale is the scarcity of human expertise required to maintain it. There are not enough trained quantum physicists in the world to staff every quantum computing facility that research institutions and companies want to operate. If AI can lower that expertise barrier significantly, the entire deployment economics of quantum computing change in a fundamental way. More institutions can afford to operate quantum hardware. More researchers gain access to it. The pace of discovery across the entire field accelerates. Meanwhile, the national laboratory deployments continue to produce concrete results with real infrastructure. Oak Ridge National Laboratory, home to Frontier, the world's first exascale supercomputer, and the machine that broke the threshold of a quintillion floating point operations per second, partnered with NVIDIA and HPE to install an NVIDIA GB200 NVL72 system at the Oak Ridge Leadership Computing Facility in early 2026. Researchers at Oak Ridge are now actively using NVQ-Link and Q-to-Q programming tools to work on quantum error correction problems and hybrid quantum classical algorithms, doing this work on site at the same physical facility that houses the most powerful open science supercomputer on Earth. The symbolic weight of this is real and intentional. Frontier represented the peak of classical supercomputing when it launched. And now it is sharing a data center with quantum processors connected through NVIDIA's bridge, beginning the transition to a new class of computing that combines the strengths of both paradigms. This is not a future plan. It is happening now. Pacific Northwest National Laboratory added its own significant milestone at GTC 2026, announcing a collaboration focused on developing tight integration between NVIDIA GH200 Grace Hopper superchips and FPGA-based quantum measurement and control systems. The PNNL team stated explicitly that they are working toward making quantum computer calculations practically useful within 5 years, and they identified NVQ-Link as the critical enabling layer that makes that timeline realistic rather than aspirational. It is also worth taking a step back to understand NVIDIA's broader strategic position in the quantum computing landscape, because it is genuinely unusual among major technology companies, and it is a large part of why NVQ-Link has been able to move so quickly and so broadly. Most of the major players in quantum computing are pursuing a vertical strategy. They are building their own quantum processors and betting that their specific approach will emerge as the dominant technology. Google has Willow, IBM has its superconducting roadmap. Microsoft is pursuing topological qubits. Amazon has its own quantum hardware initiative. Each of these companies has made a substantial bet on a specific qubit architecture. And if a different architecture ultimately proves superior, they face the risk of having invested heavily in the wrong technology. NVIDIA made a fundamentally different strategic choice. They are not building a quantum processor at all. NVIDIA is building the infrastructure layer that connects every quantum processor to classical computing power, regardless of which qubit technology ultimately wins. This is the picks and shovel strategy applied to the quantum era, named after the historical observation that during the California gold rush, the merchants who sold picks and shovels to miners consistently made more money than the miners themselves because they profited from every miner, regardless of whether that particular miner struck gold. Q2Q already integrates with approximately 75% of all publicly available quantum processors as of 2026. NVQ-Link simultaneously supports superconducting, trapped ion, spin qubit, photonic, and neutral atom architectures. NVIDIA makes money and provides value no matter which quantum hardware approach ultimately proves most capable, and in the meantime, they are making every one of those approaches dramatically more useful by giving them access to GPU supercomputing power for error correction, calibration, simulation, and hybrid algorithm execution. The total quantum computing market is projected to grow from under $1 billion in 2025 to $3 billion by 2030. NVIDIA's infrastructure model positions them to capture a significant and growing share of that value across the entire ecosystem, rather than just one segment of it. The geopolitical dimension of what NVQ-Link represents is also important to understand with clarity, because governments around the world are paying very close attention. When U.S. Secretary of Energy Chris Wright commented publicly on the NVQ-Link announcement, his language was direct and unambiguous. He said that maintaining American leadership in high-performance computing requires building the bridge to the next era of computing. And he explicitly identified the collaboration between national laboratories, startups, and companies like NVIDIA as central to that national mission. In December 2025, Undersecretary for Science Dr. Dario Gil testified before the House Science Committee and described the convergence of AI, high-performance computing, and quantum systems as standing at the precipice of a genuine scientific revolution. He outlined a federal initiative called the Genesis Mission, designed to mobilize national laboratories, universities, and industry partners to build an integrated discovery platform capable of doubling the nation's research and development productivity within a decade. China, Europe, Japan, and South Korea are all watching this development with intense strategic focus. The global supercomputing centers that signed onto NVQ-Link within weeks of its launch were not doing so out of casual curiosity. They were doing so because they recognized that access to GPU quantum hybrid infrastructure will determine which research institutions can operate at the frontier of scientific discovery in the coming decade. The countries and institutions that build out this hybrid computing infrastructure early will have a compounding head start in every field that quantum computation touches, including materials science, pharmaceutical development, and drug discovery. climate modeling, energy grid optimization, artificial intelligence research, cryptography, and national security applications. So, did NVIDIA's Quantum Bridge actually work? Here's what year one produced. NVQLink launched with 17 quantum hardware partners and 9 US national laboratories simultaneously. Within weeks, more than a dozen global supercomputing centers adopted it. Quantinuum used it to set an absolute world record in quantum error correction, achieving real-time QL-DPC decoding 32 times faster than the required threshold. Q-to-AQ became the dominant software platform for hybrid quantum classical computing, integrating with approximately 75% of publicly available quantum processors worldwide. The 43-qubit quantum optimization simulation on 2048 ampere GPUs pushed the boundary of what hybrid classical quantum computation has ever achieved. The Ising AI model family launched as the most capable quantum-specific AI toolkit ever built, with calibration performance exceeding every competing system and error correction decoding 2.5 times faster than the previous industry standard. Real-world deployments at AGIC, at Oak Ridge National Laboratory, at Pacific Northwest National Laboratory, and at institutions across 3 continents produced measurable, concrete results. Engineering time cut by a factor of 3. Calibration timelines compressed from days to hours, error correction speeds exceeding requirements by a factor of 32. This is not a technology that is still waiting to prove itself in the real world. This is a technology that delivered meaningful results in its very first year of existence and is now scaling rapidly across the global scientific computing ecosystem. The U.S. Department of Energy has set a deadline of 2028 for deploying what they call a scientifically useful quantum supercomputer, defined as a machine capable of solving real scientific problems that no purely classical supercomputer can match. The infrastructure that NVIDIA built in 2025 and expanded through 2026 is the foundation on which that 2028 goal now rests. The Ising AI models will keep improving as more quantum hardware generates more training data, and as more research teams fine-tune them for their specific processor architectures. NVQLink will become standard infrastructure in scientific supercomputing centers worldwide, the same way NVIDIA's classical GPU interconnect technology already is. And Jensen Huang's prediction will move from being an ambitious statement made at a press conference to an observable physical reality in data centers around the world. The question is no longer whether the bridge was built. The bridge is built, it is standing, and traffic is already moving across it in both directions. The question now is how fast that traffic grows. And based on everything that happened in year one, the answer is faster than almost anyone expected. If this video gave you a clearer and more complete picture of where the quantum classical computing revolution actually stands right now, not the hype, not the vague promises about a distant future, but the real engineering results and the real infrastructure being built today, then please like this video and subscribe to this channel. We will keep tracking every major development in this space as it happens, because as the first full year of NVIDIA's Quantum Bridge has just proven beyond any reasonable doubt, this story is moving faster than the world has noticed.